Hi, my name is Olivier Jeunen, and I will be presenting the paper, A Probabilistic Position Bias Model for Short Video Recommendation Feeds. This details some of the recent advances we've developed at ShareChat. Now, a first question that some of you might have is, who is ShareChat? So we are India's leading multilingual social media platform. We have around 118 million monthly active users, and we have an app which has these hierarchical short video feeds. Meaning we have a first-level scrollable feed, and the users can enter a more full-screen second-level feed via any first-level item. So this very short video should really show the point where we have a feed, you can scroll, you can scroll, you can scroll, and then when the user sees something that they like, they can tap it and go into this second-level feed. And so we have different research goals, but one is really that we want to really understand how users interact with the content that they love. Right, cool. So about position bias. Very simply put, a post that is shown at a higher rank will get more exposure than posts shown at lower ranks. And for the ranker that we have in production, we can simply measure this empirically, right? We can just really count how often we observe view events at certain ranks. Now, note that this is actually already quite different from typical web search use cases, where view events for the items themselves are not really fully observable. Okay, so what happens when we want to deploy a new ranker, right? So how much exposure would a certain post have gotten under this new ranker? Now, this is a counterfactual inference question at its core. Okay, so why would this be useful actually? Well, I think the most common application for these position bias estimates is really when you're doing offline evaluation. And it's most clear when you think of the DCG metric, right? So here you would actually sum over ranks. You would have a function that computes a gain for every item in that rank, but then there's a discount as well, which is dependent on the rank. And so that discount function is exactly the position bias that we try to model. We can also think about fairness among content creators in terms of the exposure that they get, right? If some new ranking policy is going to significantly shift this distribution, we might really want to be aware of it. And moving on from simple measurement, we can use these estimates for unbiased learning to rank as well. Right, great. So now we're convinced that this is an important problem, but hasn't this been done before? Well, I think most existing work in the field really focuses on web search use cases and on very simple equations, right? And so most famously, you have this logarithmic form of DCG, which has been widely adopted. But we can also make this slightly more general, where now we have a logarithmic form which has a single parameter alpha, which is just a bit more general now. There's also some works that use entirely different forms, where you, for example, have a exponential form where you now have a simple parameter gamma. But they're all still very, very straightforward and very simple functions. And so these are clearly the pros of those approaches. They're simple, they're intuitive, they're very efficient to compute. But the problem is that they have very limited expressiveness, and they don't really accurately represent the position bias that you would get in all possible use cases. And so for this reason, people have looked into more complex equations. And then we're typically in the field of using neural networks, right? So now we would simply have a function f of theta, which is going to take in the rank, and given the rank, it's going to output the view probability. And one advantage here is that it's very easy to extend this into a model that takes the context into account, where now we would simply pass in more inputs to the neural network. And so the main advantages here is that you clearly have a model that has high expressiveness and is very adaptable, but they are much harder to interpret, and we essentially lose some nice properties that make the model very robust when we use these neural networks. And maybe most importantly, it's very, very inefficient to want to require neural network calls each and every time someone wants to do an offline evaluation on my system. So this is also not great, but is there maybe some way that we can get the best of both worlds? Now, when we take a step back, we can think of users scrolling through the feed looking to be entertained. And so a certain scroll depth deep, they will leave the feed which will either be because they found an item that brings them to the second level feed, or because they decided to abandon the app altogether. And so the main question that we want to ask is whether we can somehow model this scroll depth distribution to inform the sort of estimates for the position bias that we care about. Now, because most people will actually enter the second level feed via a very highly ranked post, we see that this scroll depth actually follows a discrete parallel distribution. And one known distribution that fits these requirements is the Ewell-Simon distribution. And that looks like this. So what I'm showing here over the x-axis is simply the scroll depth and the probability mass function for the distribution on the y-axis. And it has a single parameter rho, which we can set to represent very different scrolling behaviors. Now, so going from scroll depth to the position bias, we can say that a rank R is viewed if and only if the user scrolls down to at least that rank. And so this quantity is known as the survival function of a distribution. And for Ewell-Simon, it's going to look like this. It might look a little bit scary at the beginning because there's a beta function in there, which we don't see very often. But in essence, it's a simple function that really just is going to take in a single input parameter rho. And so now we have an efficient single parameter equation that is at least rooted in a sound theoretical model of how we believe users behave. Okay, so what do the curves look like, actually? Well, they look like this. So here I'm showing the rank over the x-axis and the viewing probability for that rank on the y-axis. So we first have three simple baselines and then a range of different functions based on the Ewell-Simon distribution with a varying parameter rho. And the first thing that we see is that the classical DCG discount and the logarithmic form that we deduced from it, they really don't discount strongly enough. They still give a higher than 10% viewing probability at rank 100, which is really just very, very different from what we observe in our systems. Now, the other form that we look at, the exponential functional form, really just it models very different user behavior than the behavior that we actually care about here. Okay, cool. So we have the system, we can represent very different functions, but we still don't have the advantages of the neural network approach, where we can just plug in some site information, essentially, that is going to allow us to condition on that. And so we can just replace the single parameter rho by a function rho. And so this now looks very, very similar to the neural network approach, right? We now have a function, we learn that function by maximum likelihood estimation, but the main advantage that you get here is from the inductive bias of having this fully probabilistic framework, which is going to make it much more sample efficient and much more parameter efficient. Whereas normally your function would have to take in the rank and output the position bias at that rank. In this framework, we just need a very, very simple function that maps it to a single scalar, and this scalar goes into the Ewell-Simon distribution. Okay, so does this actually work, right? We look at two different tasks. So the first use case is whether we can actually model empirical exposure more accurately with the new model that we're proposing. And the second task is whether we can actually use these obtained position bias estimates for downstream tasks, such as doing offline evaluation with DCG. We ran experiments on data sets that we collected on our own platform, because these things are very, very use case dependent. And so there's really no data sets out there that we would be able to use for this. Okay, so the first thing to do is to see whether the models actually represent empirical data better. And so for this, we use the negative log likelihood. I don't think that this is the most interesting slide that we have, but we can really see that for both the non-contextual and the contextual use cases, the newly proposed method that we have is really able to come up with the most accurate estimates, which is promising. But when we look at offline-online alignment, I think things get a lot more interesting. So what we show here in the table is the correlation between the offline metric estimates that we have and the online metrics that we actually get from running A/B tests. And we can see that by adopting our newly proposed method, we see a significant increase in the correlation, which is a very, very encouraging signal. All right, to conclude, I think position bias is very important, but it's also very use case specific. And so blindly adopting this very, very simple sort of logarithmic curve that was proposed in the original DCG paper might not really be the right thing going forward. And so we've shown that using probabilistic models can really give rise to very efficient and very effective alternatives, and that they can lead to improved offline evaluation and stronger offline-online metric alignment. Okay, then I would just like to thank you all for listening. I'd be happy to answer any questions. Feel free to reach out to me offline as well. Thank you.